Hello, this is the final part of the time value of money. We are going to we'll go to following learning goals. The first one is understand the effect that compounding interest more frequently than annual has on future value, and this is basically called the effective annual rate of interest. Now, basically, we look into compounding and effective annual rate, how to compute it. And then we'll look at the second learning goal, which is to describe the procedures involved in determining deposits needed to accumulate a future sum, loan amortization, finding interest or growth rates, and finding an unknown number of period. These two, the last two, the number 3 and 4 has already been discussed in the at the end of the first session, first part of the uh, TVM. However, we'll again look into this as a refresher. This So far we had looked at compounding annually. Annual compounding means was if I have a timeline, I would say that we have $100 at the end of year one, and then we have at the end of year two, whatever we receive, we keep on investing, we do nothing, we keep the amount here, and then we exit at year three, at the end of the year three. So the 100 first accumulates with 8% interest rate, and then the total amount, which is 100 of 8%, which is 108. This will be reinvested for another year, and that will be at 8%, and that will becomes 116.64. So basically it was annual compounding, but we call compounding basically when compounding is more frequent than once a year, right? So within a year there are interest on interest. So this example that I show you was interest on interest across the years, but this is within a year. And if it's within a year, then the results is a higher effective interest rate because you are earning on interest on interest more frequently. And because of this, you will have your effective interest rate should be greater than the nominal interest rate, which is simple interest rate. And let's look at an example. So you have future value from investing $100 at 8% interest compounded semi-annually over 24 months. Now for 6 months, it will be $104. So you can see that 8% is 4%. So we divide the interest rate, 8% divided by 2, which is 4% per time period. Since it's semi-annual, so we divide by 2. This is the semi-annual comes here, and we get this per semi-annual time period. So with this, we have a timeline like this, which is starts with 0, then we have 6 months, then we have 1 year, then we have 1 year 6 months, which is 12 months. We can write here 12 months, and then we have there 18 months, and then we can have here 24 months. This is basically 1 year, and this is 2 years. So basically it accumulates from 6 months, and then 6 months to at the end of the 6 months we have 104, and then we have 108 and 108.16, and then we have 112.49, and at the end of the second year we have 116.99. So we have basically within 1 year we have interest on interest, and then we have this also interest on interest. Similarly, if we are doing it quarterly, we are going to divide the 8% by 4, and we'll get 2% per quarter. per quarter, and over 24 years, here's the schedule. And at the end, you will get 117.17, which is way more than if you invest for 2 years, $100 at 8%. Let's look at that. So future value annually, if you invest at the end annually, you will have 108. Semi-annual compounding, which means once compounded within a year, will be 108.16, and quarterly will be 108.24. So you can see that these are increasing as we increase the from semi-annual to semi-annual and semi-annual to quarter. This is 1, this is 2, and this is 4 quarters. So the number of quarters increases, so number of interest on interest increases, and hence you have a higher value. Similarly, if you look at 116, it will be 16.64, 116.99, and here it is 117.9, which is also increasing with the increase in compounding period. Now we can see that we can draw a general equation, which is basically future value of n equals to present value multiplied by 1 plus r divided by m n into m, where m is the compounding time period. So for instance, if we have, for the same example, for semi-annual, what we will do is future value of for 2 years equals to, it's $100 multiplied by present value is $100, and then we have 1 plus 0.08 divided by semi-annual compounding, which means 2, and then we have n is 2 years multiplied by 2 compounding, semi-annual compounding, so this is n and this is m, and that will give us a value of $116.99. Similarly, if we want to do it for quarterly, then it will be FV for 2 years equals to $100 multiplied by 1 plus 0.08 divided by, now we are going to divide by 4, and 2 into 4, so this 4 is the m and the 2 is the n, and this will give us the value of $117.17. So interest is divided while number of time period is multiplied. You can see this, we can also calculate with the help of the calculator, and we'll have the solution by using the simple TVM functions. The noteworthy is that n is 4 and I is 4 for semi-annual, and now is have n is 8, so this you are going to do it manually. N is 8 and I will become 2 per quarter. This is per quarter and this is per semi-annual. Same you can do it with the with Excel. You can see that these are the inputs, these are the formulas that can help you to calculate the values, 116 for semi-annual and 117 for quarterly compounding. Now we have the general form of continuous compounding. Continuous compounding involves the compounding of interest an infinite number of times. Number of times per year at interval of microseconds. At interval, very small interval of microseconds. Sorry for my writing, I'm trying to be as clear as possible. So the formula for that will be future value of n is equal to present value multiplied by the exponential. We use the exponential function r into n, and exponential function, this is exponential function, An exponential function has a value of 2.7183 and so on and so forth. So we have an example. Find the value at the end of 2 years, which is n is equal to 2. FM's $100 deposit, present value is $100 in an account paying 8% annual interest rate, compounded continuously. So in microseconds it's compounded. So it will comes out to be future value 2, and since it's a continuous compounding, I'll make CC continuous compounding equals to, and that will be present value multiplied by ERT, and that comes out to be $100. Substituting for present value and then substituting for R and T, we get e raised to power R is 0.08 multiplied by T is 2 years. That comes out to be 117.35. So if continuously compounded for 2 years, you will get receive $117.35. In calculator, you have a function which is called, when you use the second function and press EX, you can get it. So first you have to input, then you have to press function, then you have to press EX. You will receive this number. When you multiply with the principal value, you get the total $117.35. Same is the case. You can see that there is an exponential function in Excel which helps you to calculate this, and this is the solution. Nominal and effective annual rates of interest. Now after compounding, we have a little bit of idea of how the investments increases at a higher speed when it is compounded more or compounded at a higher frequency within a year. So the nominal interest stated annual rate is the contractual annual rate of interest charged by a lender on promised by a borrower. We also call it simple interest rate. The effective or true annual rate is the annual rate of interest actually paid or earned. And effective rate is normally greater than the nominal rate whenever compounding occurs more than once per year. So this is also called APR, annual percentage rate, and EAR is always greater than APR because of compounding. Now let's see how it works actually. Let's look at an example. So FM wishes to find the effective annual rate associated with an 8% nominal rate, and the interest compounded at annually, semi-annually, and quarterly. How do we calculate EAR? So EAR is calculated as equals to 1 plus R over M minus 1. Now this will give us the effective annual rate, and for the effective annual rate to compute with these three values, we can do first one, which is EAR equals to 1 plus 0.08 divided by 1. 1 is for annual, raised to the power 1 comes out to be 0.08 or 8%. So it's the same as the APR or simple interest rate. So ER and APR are same when there is one period compounding. Now let's see semi-annual compounding. In semi-annual compounding, we have 1 plus 0.08 is 2, and raised to power 2 equals to, this is 0.0816, that comes out to be 8.16%. So it's now increasing, and it's increasing because the compounding is increasing, and I can show it from here, from 1 to 2 it's increasing. So as M is increasing, this is M equals to, and this here also, this is M equals to 2. It's increasing as the compounding is increasing within the year, and so the value is also increasing. Let's go back and see the third one. For quarterly, EAR equals to 1 plus 0.08 over quarter, 4 quarters in a year, and then we have 4. This gives us, sorry, I have missed minus 1 and minus 1, which is, so this comes out to be 0.0824, and it's even higher, which is 8.24%. So further increasing, and this shows that compounding has an incremental effect. So let's look at some special application of time value. Now, suppose you want to buy a house 5 years from now. This is N, and you estimate that an initial down payment of 30,000. This is the will be required. So it will be required in the future. Is future value. To accumulate $30,000, you wish to make equal and annual end of year deposits. This is what we call annuity, because they are equal, and end of year, so it's ordinary end of year annuity into an account paying annual percent 6, which is R. So how do we compute? We already have a ordinary annuity formulas for both present value and future value. Here we need future value, so we are going to pick future value of annuity equals to cash flow multiplied by 1 plus Rn minus 1, and then we can have this divided by R. So since we have a requirement to calculate future value, we are going to rearrange the formula, and that would be cash flow equals to future value of N, and then we will have divided by the entire value, which is 1 plus R N minus 1 over R, and we will get the annuity amount. In order to do so, we will substitute the value, and that comes out to be future value is $30,000, and this will be divided by 1.06 raised to the power 5 minus 1 divided by 0.06, and the eventual answer is $5321.89. So this is the amount that we have to deposit each year. Let me pick this is the amount that we have to deposit each year in order to accumulate $30,000 so that we can buy the house in 5 years time. Similarly, we can see that in examples we can see that using the TVM calculator we can have a future value which is 30,000 and 5I, interest rate is 6%, compute PMT. It automatically calculates you 5321.89. This is a pretty fast one. Same, you can do it in the Excel sheet, and you can see that for this you have to calculate the PMT value, PMT function. You can use the PMT function to calculate it. Another special application of time value is loan amortization. Loan amortization is the determination of equal periodic loan payments necessary to provide a lender with a specified interest return and to repay the loan principal over a specified period. Now, the loan amortization process involves finding the future payments, and this over a certain time period whose present value and the loan interest rate equals the amount of initial principal borrowed, and whatever happens here is actually displayed and in a form of a table or schedule, which is called loan amortization schedule. Since the payments are equal, so it's a annuity type problem. Let's look at it how it works. Let's look at an example. Say you borrow $6,000 at 10% and agree. So we borrow at 6,000 right now. This is the present value. 10% is the R, and agree to make equal end of year payments. So this is what we are going to find out. This is the annuity and it's the year end, so it's the ordinary annuity. 4 is the time period, and to find the size of the payments, the lender determines the amount of a 4-year annuity discounted at 10% that has a present value of 6. So this is actually restating the same problem. What is the present value of annuity formula? So we can write present value of annuity, which is CF over R multiplied by 1 minus 1 over 1 plus R. This is the present value of ordinary annuity. We can convert this into um, since we need equal amounts, so we need cash flow on this side and the other. So we multiply, this is present value, multiply by the R and divided by. So this is divided by 1 minus 1 over 1 plus R N. Now in order to solve it, we will have present value, which is $6,000, multiplied by 10%, which is 0.10, and then we have to divide it by 1 minus 1 over 1.1, 10% is to power 4 years. This will give us an cash flow of $1892.82. Now we can use this amount to construct an amortization schedule, which is given in the next slide. However, before we go to that, you can also calculate the same with the TVM calculator, time value of money functions you can use, and you have input of 6,000 as present value, n is equal to 4 and I is 10%. You can press compute, get PMT, the solution is given. So basically PMT is much faster with the TVM calculator. Similarly, you can do this in the Excel. You have to use the PMT function, in which first you have to provide the interest rate, and then you have to provide the number of years, and then you have to provide the present value or the cash flow, whatever the present value cash flow amount. The rest of them you will leave it blank, and you will see that you can get a number minus 1.1892, or which is the outflow. The negative sign shows the outflows. Now let's look at the schedule. So we have 6,000 principal, 10% interest rate, 4-year repayment period, and we already calculated this. The cash flow or the annuity comes out to be $1892.82. We can use this amount as loan payment. Now this has two parts, interest and principal. So we begin with 6,000 as the borrowed amount principal. Now this will start going on. So next is loan payment. Now we will pay 1892.82 in the first year. At the end of the first year, what are the parts of 1892? So it has $600 and it has the two parts principal. So if you add both of these two, you will get 1892. And so interest is calculated at 10%. You calculate interest 10% multiplied with the principal. So this is the 600 comes out by multiplying 6,000 with 10%. So this is 600, and principal is simply subtract the 600 from the loan payment. Whatever is left is reduced as part of principal. End of year principal is when you subtract 6,000 and 1892, you will get 4707. This becomes the beginning year cash flow here, and so on and so forth. It will again subtract 1892, and 470 is calculated by multiplying this amount 47 with 10%, and the result goes to here. The result goes here, and 470.72. The remaining is 1422, which is the principal, and for the total balance left is this much. At the end of the fourth year, we should get nothing here. It should be 0 or a very small amount. Sometimes the small slight differences comes because of the rounding off errors, and that's all right. In Excel, it's pretty much straightforward. We already calculated 1892, the plan in the last to last slide. However, you can construct a schedule by designing this way. You have loan principal amount, loan annual interest rate, number of years, and annual annuity payments, which is 1892.82. And then interest is computed based on the remaining principal balance at 10%. That's calculated principal whatever when interest is subtracted from the total money from the total it will get what is remaining, and so end of year principal is calculated, and which becomes the beginning year of balance. So these are the computation you can do, and it's much easier on the Excel. However, the concept is same everywhere. Another special application of time value of money is finding interest or growth rates. We already discussed it. It's CAGR at the end of the first session, which is basically we calculate from future value equals to present value multiplied by 1 plus Rn, and we rearrange the formula to get R equals to future value n over present value 1 over n minus 1. This is compound annual growth rate, and I think you can go back to those the first video of time value of money, and at the end you can see that we have applied it to a stock market fund as well to see how it is used. We can do one more example with this, and the example is that Ray Noble purchased an investment 4 years ago for 1250. Now this 1250 is the present value and 1520 is the future value. It is for this what compound growth rate, as I said, this is CAGR, has earned return on this investment. So plugging this into equations we can get so this is R is equal to future value divided by present value 1 over n minus 1, and this comes out to be so right now 1520 divided by 1250 1 over 4 minus 1 comes out to be 5.01% per annum or per year. In calculator it's pretty straightforward. Present value is given, future value 1520, and n is 4 years. Compute I. So this is what we compute I, and you will get 5.01, and same is the case with the Excel, where you can calculate the I using the rate function. Then we have another special application of time value of money, which is interest rate. So finding an unknown number of periods we have already done again at the end of the first TVM session. You can go through it again to refresh the concept, or just to refresh here, it is the n equals to log of future value over present value divided by log of 1 plus R. Now this is what we have used in order to calculate, sorry I should not mention here, n equals to, this is the idea. The simplest case would be when a person wishes to determine the number of periods n it will take for initial deposit and to grow to a specified future amount. So to grow to a future amount given an interest rate R, and we can do an example. For instance, there is a 1000 deposit earning 8%. So this is $1,000 earning 8% per annum, and we have the future value would be $2,500. So how many years it should remain invested? So we can plug in and we can see that n equals to log natural or log of future value divided by present value, which is 2500 divided by 1000 and then log natural 1.08. This will give us a value of uh, 11.91 years, or approximately 12 years. The example is also done based on the TVM calculator, and you can see the TVM calculator also gives the same amount. If you input present value 1000, future 2500, I 8 years, and compute for n, it will be around 12 years. In Excel, it gives the same way. If you use the NPR function to calculate this, we'll get around 12%, 12 years, sorry. Another example can be done, and you can see that in this example BST can borrow $25,000 at an 11% annual interest rate, and uh, equal annual end of year payments of 4,800 are required. He wishes to determine how long it will take to fully repay the loan. So this is basically equal annual end, means this is an annuity and it's an ordinary annuity. Now he wishes to determine how long it will take to fully repay the loan. In other words, he wishes to determine how many years n it will take to repay 25,000 11% loan PV if the payments of 4,800 are made at the end of each year. So you see present value is 25,000 he borrowed, payments are 4,800 equal, and I is 11%, and we see that it takes 8.8 years to actually repay the $25,000 loan. This is basically you can use the annuity, ordinary annuity formula, and it can be done with it's possible to do it with the hand as well by switching different values for n. In Excel, it can be done with this NPR, and you will get 8.15. So we finish with this time value of money concepts. The final concept that we have gone through are related to compounding interest more frequently than annual, and also effective annual rate of interest. We also looked at the different application of time value of money, such as determining deposits need to accumulate a future sum, which use the future value of annuity formula, loan amortization, which use the present value of annuity formula, and then we have used growth rate, which is CAGR, and finding an unknown number of periods in formulas. So these are all the learning goals that we were expected to cover, and now practice would actually let you to become perfect, or to perfect this skill. So I would strongly recommend to practice as many questions as possible in order to understand the scenarios in which these problems can come and can be solved. Thank you.